Swayam Prabha. Digital India. Educated India.
So, today we will start from where we left in the last lecture. We were solving a problem of free recovery. So, there was a string shape memory alloy wire. So, that was fixed at one end and free at the other end, and the other end had a weight attached to it. So, we saw what is happening when it is heating up, and we saw the strains as per both the Liang and Rogers model and the Tanaka model. Now, we have to see what happens to it when it is cooled down. Now, the temperature is heated up to 77 degrees centigrade, which means it crosses the austenite finish temperature, and that means that it becomes fully austenite, and then the cooling process takes place. So, if I look at the diagram once again, this is our temperature and this is sigma. So, we were along this line. So, we are heating it up and we are somewhere here, and this temperature we found it to be 75.5, whereas we heated it up to 77 degrees centigrade. That means the material became fully austenite, and then the cooling takes place. So, you have to find out when it is fully austenite what was the amount of strain here. So, to do that, again we can write the equation, constitutive equation. If I write it fully, so sigma minus sigma 0 is equal to E multiplied by epsilon minus epsilon 0 plus omega multiplied by xi minus xi 0. This quantity is 0 because initial and final stress are same, stress is maintained to be constant, and in this case, so we are finding it at AF star, which means at the point where austenite formation is just finishing. So, at that point we know that sigma should be close to 1, sigma should be 1 ideally, and 0, sorry, it is not 1, it is 0 because the austenite finish has taken place, and here it started with a martensite, fully martensite. So, it is 1. Epsilon I have to calculate, epsilon 0 is where we started from, and the epsilon 0 at that condition was 4.24 multiplied by 10 to the power minus 3. Now, because we have reached the austenite condition, E is just EA, and accordingly omega is minus epsilon L multiplied by EA. So, everything is known in this equation except for epsilon, and this quantity as we know it is 0. So, if we solve for it, the epsilon comes to be minus 0.06276, which means this is the strain at the austenite condition, at the austenite phase. Now, when we cool it down, we are starting from the austenite phase, which means we are, while cooling it, my initial strain should be 0.06276, while when the martensite formation takes place in this zone, if I want to calculate the strains at different temperatures, my initial strain should be taken as this, the austenite strain, which is minus 0.06276. So, before we do that, we have to find out the xis. So, xi as per Tanaka's model, and we are calculating it at T is equal to 48.5 degree centigrade. So, at that time our xi is given by this equation. We know that xi t when the Martensite formation takes place is equal to 1 minus e to the power a m ms minus t plus b m multiplied by sigma. Here sigma is equal to sigma 0, the same stress that is there constant throughout. Now, in this case a m as per Tanaka's model is natural log of 0.01 divided by ms minus mf, and that gives it as minus 1.6447 per degree centigrade, and Bm is Am minus Am by Cm, and that is equal to minus of 1.6447 divided by 12, and we get the quantity as minus 0.137 per megapascal. So, accordingly xi is calculated as 0.9717, in percentage it becomes 97.17%. Now, we will do the same calculation as per Liang and Rogers model. So, xi as per Liang and Rogers model and our T is again 48.5 degree centigrade. As per Liang and Rogers model, the formula is xi t equal to 1 minus xi a, and in this case because we are starting from a fully austenite condition, so xi a is 0 anyway. So, we can directly write that as 0. So, we can call it half. Half multiplied by cosine of a m t minus m f plus b m sigma plus half. Now, here a m is pi by m s minus m f, and that is 1.122 per degree centigrade, and B m is minus A m divided by C m, and that is minus 0.0935 per megapascal. So, now xi at 48.5 degree centigrade becomes 0.8804, which is 88.04%. So, that is my xi as per Liang and Rogers model. Now, we have to find out the strengths. We have already defined the initial conditions. So, now the equation is sigma minus sigma 0 equal to E xi multiplied by epsilon minus epsilon 0 we are neglecting the effect of phi as usual. So, it is omega xi multiplied by xi minus xi 0. Then we have E xi, then we have xi minus xi 0, epsilon minus epsilon 0. So, epsilon minus epsilon 0 was calculated as minus of 0.06276. So, it becomes plus 0.06276, and then we have minus epsilon L multiplied by E xi, and then xi 0 is 0 because we started with a fully austenite condition. So, it is just xi. So, this equation we would use. Only thing is that xi has to be calculated once using the Tanaka model and once using the Liang and Rogers model. So, now let us do strain calculation. Using Tanaka model. So, to do the strain calculation using Tanaka model, all we have to use is we have to just find out the xi that is obtained from the Tanaka model. So, if I put it in the equation, it is 0 is equal to E xi. Now, E xi should be calculated first. So, E xi at this condition is E xi. So, when xi is equal to the xi that we obtained from the Tanaka model was xi is equal to xi is equal to 0.9717. So, at that temperature, at that xi, E xi becomes 21 GPa. And then accordingly omega xi becomes minus epsilon L into E xi, and that comes as minus 1.470 GPa, minus 1.407 GPa. So, if I now put everything here, the equation becomes E, in the same equation, epsilon plus 0.06276, and then we have minus epsilon L E multiplied by xi. Xi we know E, we know epsilon E and everything. So, finally, after solving, the epsilon comes to be 0.00234, and if this is the epsilon, then my delta L is L multiplied by epsilon, and that gives a value of 0.0208. So, L final is L plus delta L, and that is 0.321 meter, which means the tip position of the wire at this temperature while cooling down is at a distance of 0.321 meter from the fixed end. Now, we will do the strain calculation using the Liang and Rogers model. Everything remains same except xi becomes different. Liang and Rogers model and we are doing strain calculation. Using Liang and Rogers model. So, in this case the xi that we got was 0.8804 and as per that our E is, if we apply the same formula, our E comes to be 25.89 GPa and accordingly omega comes to be minus of 1.735 GPa. Then we apply the same formula, we have 0 is equal to E multiplied by epsilon plus 0.06276 minus or we can say plus omega which is minus of epsilon L into E multiplied by xi. So, then we can solve it and we can find out our epsilon. Once we get our epsilon, we can again find out the tip position at that temperature. So, this completes the problem. So, again to summarize, because it is a free recovery problem, we could find out xi at each temperature during the transformation and xi gave us the elastic modulus and omega, and then if we put it in the constitutive relation with proper initial conditions, we can find our unknown in the problem, which is our epsilon. So, now we will look into another problem, that is a constraint recovery problem. So, here is the problem. We have a shape memory alloy wire of length 0.3 meter and circular cross section with diameter of 0.5 millimeter is fixed at one end and connected to a linear spring of stiffness K is equal to 2000 Newton per meter at the other end. The wire is at a temperature of 15 degree centigrade in Martensite phase. So, it is a Martensite phase. And then we have to find out the stress in the wire when the temperature is elevated to 60 degree centigrade. So, here the entire arrangement looks like this. We have a fixed end from which we have a wire coming out and then it is connected to a spring. The spring has certain stiffness and the spring is held here. So, when this wire tries to expand or contract, it is resisted by the spring. So, it is not a, the spring is the wire is not free. So, when it is heated up, it tries to recover, but it is not a free recovery because of the resistance offered by the spring. So, here if I again draw the phase diagram, in the previous case the stress was constant and everything was happening at a constant stress. Now, here initially the stress is 0. So, when I am heating it up till the austenite start temperature, the heating is 0. After it crosses the austenite start temperature, xi changes and accordingly it would try to shorten, and when it would try to shorten, the spring would give some resistance and that would generate some stress, tensile stress. So, some stress comes into picture here. So, instead of following this 0 stress line, now it would go towards some non-zero stress value, and again because of the stress xi changes and as xi changes the strain would try to change, and at the same time temperature is also changing. So, strain would try to change and that would again affect our stress. So, it becomes a non-linear problem. So, instead of following this route directly from AS to AF, it follows a route something like this, the transformation. So, that we would quantify it and see it numerically. So, now let us establish the mathematical relations here first. The spring has a stiffness of K. So, if we say that the force acting here at the junction between the spring and the wire material is F, then we can write that the strain in the material is E is equal to minus L minus delta L by L, change in the length by the initial length, which should be is equal to minus of F by K L if I look at the spring, because K is the spring constant. So, F by K is our delta L, and then F is also nothing but sigma into A, where in the string, stress in the string, stress in the wire multiplied by A, and that becomes minus sigma A by K L. So, from this we can find out our epsilon as minus sigma A by K L. Now, if I look into the constitutive relation, it is sigma minus sigma 0, and that is equal to E as a function of xi multiplied by xi minus xi 0 plus omega xi multiplied by xi minus 1. Now, xi 0 is equal to 0 because there was no force applied, and till it reaches AS there is no transformation. So, there is no change in length. So, xi 0 is 0, and accordingly sigma 0 is also 0. Now, we can write sigma is equal to E of epsilon multiplied by epsilon, E of xi multiplied by epsilon, and epsilon we already saw that it is minus of sigma A by K L, and then we have epsilon L E xi multiplied by xi minus 1. So, this is a complicated equation because we have sigma here, we have sigma here, and also our xi is again a function of sigma. So, xi is e to the power A multiplied by As minus T plus B A sigma. So, here we have, and that is as per Tanaka model. So, here we have xi as a function of sigma. So, if I put it here, this becomes again a function of sigma. So, this is a nonlinear equation in terms of sigma which needs to be solved. Now, this kind of equation there are many methods to solve it. So, here we will solve it using the Newton's method. So, to do that we define a function sigma, a function f of sigma, which is equal to xi minus the entire right hand side, which means a residue. So, sigma plus E of xi multiplied by sigma A divided by K L plus epsilon L multiplied by E of xi multiplied by xi minus 1. So, ideally when sigma is at the, when sigma is solved properly, then ideally this f sigma should be 0. So, this equation we will solve using the Newton's method, Newton's absence method. So, for that what we do is start with initial guess. initial guess sigma 1, and then we evaluate f of sigma 1, and if f of sigma 1 is not satisfactorily close to 0, then what we do is we make a new guess sigma 2 equal to sigma 1 minus f of sigma 1 divided by del f by del sigma at sigma 1. Again we check whether sigma 2, if I take sigma 2, then f sigma 2 is close to 0 or not. If not, again I make a new guess, and it continues until and unless I get f sigma to be very close to 0. So, in this case f of xi, f of sigma, or sorry, f prime of sigma or del f by del sigma that we get is 1 plus E of xi multiplied by A by K L. So, if we put everything and then if we differentiate the entire expression by sigma, then the expression comes to be this sigma A by K L multiplied by E m minus E A multiplied by B A xi plus epsilon L multiplied by E xi multiplied by B A xi plus epsilon L multiplied by xi minus 1 multiplied by E m minus E A multiplied by B A xi. So, this is del f by del xi, which we need to evaluate at each iteration for the current value of the sigma. Now, let us start with sigma 1 equal to 200 Newton per meter square. So, at that sigma equal to sigma 1, we have f equal to minus of 1.6803 into 10 to the power 9 and del f by del sigma at sigma 1 equal to minus of 8.2990, and then we have sigma 2. We apply the same formula, and then we get sigma 2 from sigma 1 and f and del f by del sigma, and sigma 2 comes to be 1.6747 multiplied by 10 to the power 7 Newton per meter square, and at that stress we again evaluate our f sigma 2, and again we evaluate our del f by del sigma at sigma 2, and we continue it. Then we see that at sigma 6 we get our value as 1.9413 into 10 to the power 7 Newton per meter square, and at this value of sigma the residue function f comes to be quite less, which is minus of 1.148 into 10 to the power minus 7. So, we start with a residue of in the order of 10 to the power 9, and then we came at 10 to the power minus 7 in just 6 iterations. So, this is quite satisfactory. So, we can say that this is the value of the stress for this condition at that temperature. Now, that is how the entire transformation takes place. Here we can see how the entire system evolves. So, at the temperature 52 degrees centigrade, which is our AS, the transformation starts. So, stress is 0 still here, then gradually as the temperature increases, the stress also increases, and it increases in this fashion, in this nonlinear fashion. Now, what if I change my spring stiffness? When the spring stiffness is 0, which means in this case when the stiffness is 0, that means the stiffness is not existing. In this case, our shape memory alloy wire is free to move. So, in that case there is no stress generated. So, we can see that it is 0. Now, as we keep increasing the stress, as we keep increasing the spring stiffness, the stress starts increasing at a certain temperature. So, this is for a fixed temperature, this graph is drawn. Now, but the slope of this curve becomes less as we go on, which means that after a high value of stiffness, this almost becomes like a fully constrained end. So, after that there is no further significant change in stress that we observe if I keep increasing the spring stiffness to a very high value, and that is what we can see here. So, when k is equal to 0, it is like a free end. So, the shape memory alloy is free to expand or contract. When k is equal to a very high value, it is almost like a constraint end. So, there is no strain possible and the stress is very high. In between them, if k varies, we can see a graph like this. So, with these two examples, we would like to finish these lectures on the constitutive relations and their uses here. Now, we will gradually move to some applications. Thank you.